Okay, so I'm going to talk about implicit differentiation, and this allows us to take derivatives without having to solve something for y, especially when solving something for y might be virtually impossible with the methods that we have ourselves. So let's take a look at an example of kind of why this is so important and why we need to have this idea. So we have a question: find the slope of the line tangent to the unit circle at a certain point. So the important thing to remind yourself is that the unit circle is a circle. I want you to think about its center and its radius. Think about that. And the big thing to remember is that this is not a function. Not a function. So because of that, in order to find the derivative of this, which we would need to find the slope of the line tangent to it, we would need to basically find out what it is as a function, write that as a function. So we're looking for a derivative, specifically at the x value root 2 over 2. But of course the big question is, how do we find y prime? How do we find that derivative? So the problem is, as I already said, that the graph of this is not a function. It's not a function. And that's because, as we already said, it's a circle. So we can draw that circle, so do the best you can to draw your circle. Don't think I'm making anything special here, because I'm not. I'm just going to draw that circle. Center is 0, 0, and radius is 1, so it's going to look something like this. This is your x squared plus y squared equals 1. And if you've thought about it, you recognize that it's not a function. Visually, you can see it doesn't pass, as we talked about on probably one of the first days of class, the vertical line test. So this is not a function. However, if I were to only look at the top half of the circle, well, that would be a function. Or I could look at just the bottom half of the circle, and that would be a function. And we know that we can take this circle, x squared plus y squared equals 1, and by doing just a couple steps, we can solve this for y. And what I'll normally see is students do this. If I was to say solve this for y, they would do this. We want to remember that this is plus or minus that. So when we look at the top half of the circle, that's when y is the square root of 1 minus x squared, because the square root of anything in our case is what kind of number? Positive. The bottom half of the circle, where all the y values are negative, would be the negative square root of 1 minus x squared. So one way that we could find the derivative of this is by taking the derivative of each of those two slightly different y values, and that would tell us the slope or the derivative of the top part, and then we could do it again and find it for the bottom part, and that would be one way to find y prime for this, x squared plus y squared equals 1. So the terminology that we're going to see is when we see y equals, say, the square root of 1 minus x squared, in a case like this, y is defined explicitly. So it's defined explicitly, and I'll say with independent variable x. Now in this case, y is a function of x. I mean, this is a function and x is the independent variable, and that allows us to find y. When we see something like this circle, y is defined implicitly, and x is still the independent variable here. However, the idea here is it is not solved for y. It is not solved for y. And so it is not defined explicitly, it's defined implicitly. It's implicit that y is the dependent variable and x is the independent variable. So what we already saw was that we have two different pieces here for y. We have the square root of 1 minus x squared when y is greater than or equal to 0. And we have negative square root of 1 minus x squared. And you can imagine when that is true, y is less than 0. So to take our derivative, basically we just take the derivative of each of those pieces. So I'll do a little bit of work over here just to remind you what those are. You can rewrite 1 minus x squared to the 1/2, and you have negative 1 minus x squared to the 1/2. So when looking at those, we'll take the derivative of each of them. And that's going to require what rule that we already learned? It is the chain rule. So in using the chain rule, I'm going to bring down that 1/2. This is for the top piece, the square root of 1 minus x squared. I bring down the 1/2, I get 1 minus x squared. I get to the negative 1/2, and that gets multiplied by the derivative of the inside, which is negative 2x. So again, that's me using the chain rule. And that is when y is greater than or equal to 0. And then I'll do one more line here. Okay. Just to simplify this, the 1/2 and the negative 2x simplify to get negative x. And then that's divided by the square root of 1 minus x squared. And that's, of course, when y is greater than or equal to 0. So if you want, you can pause it and just take the derivative of the second piece here, the negative square root of 1 minus x squared. It's very similar. So if you want, pause it, do that, and then come back and take a look. So the only difference here is we have that negative in the front. So it's really the only difference. Nothing else exciting is happening here. So again, I'm taking the derivative up here, and I'm going to have the negative this. And then this is going to give me still that same negative 2x. And that's going to be for y being less than 0. And so when it's simplified, you can see it's almost exactly the same. You just have x square root 1 minus x squared, and that's when y is less than 0. So notice that what it's telling us is that for the top piece, you have a negative x, and for the bottom piece, you have an x. And so it's really just dependent on your x value. So in the numerator, if your x value is positive, your derivative is negative. If your x value is negative, your derivative is positive. And then that's the opposite for the bottom part. And you can kind of think about the tangent lines that you'd have separating the negative x values from the positive x values, and those answers should make sense. So then if we want to find the derivative of this function at root 2 over 2, we think about the fact that that's actually when you think about root 2 over 2, remember the y value was also root 2 over 2, if you go back to the top of the page. And so that's in our first quadrant. So because it's in our first quadrant, we realize that that would be this top piece here, that we'd care about the derivative right here, because that's when y is greater than or equal to 0 is at the point root 2 over 2, comma, root 2 over 2. So all we have to do then is write this as, it's going to be a little algebra here, but negative root 2 over 2. So I'm plugging this in from over here. So I'm taking this piece and I'm just plugging in that x. So root 2 over 2, and then that's going to be divided by the square root of 1 minus root 2 over 2 squared. I don't know if you can hear that outside, but somebody has decided to take this opportunity to do something, I don't know, some sort of construction. So in the denominator, we have 1 minus, and then you take root 2 over 2 and you square it, and that's going to give you 2 over 4, 1/2. and then you do the square root of 1 minus 1/2. And so that may be obvious to you or may not, but that's going to give you the square root of 1/2, or 1 over root 2, which is rationalized root 2 over 2. So what we actually get is just a -1. I mean, that's it, just -1. So it's telling us that the slope of the line tangent to this circle at root 2 over 2 is -1. And if you come back to the top here, you'll see that root 2 over 2, it's somewhere over here. I don't know exactly. And we do see that if we were to draw a tangent line, it would be a negative value. So we're not too surprised to see that it was -1. Okay, so coming back over here, I'm going to move forward to the next piece. This is the bottom of your page. It says find the derivative of this crazy thing. Okay. Now imagine trying to solve this for y, because in order to find the derivative explicitly, you'd have to have it y equals. That would have to be possible. And you can see that in this case, like, how are you going to do that? You'd have to square the left-hand side, you'd have to combine like terms, and then you're gonna have like a y to the 4th and like y squareds and all these things. I mean, this is virtually impossible. So the whole point of implicit is that you don't have to do that, especially when you can't. You don't have to do it. You can take the derivative using the idea of implicit differentiation. And that's what this whole thing is about. So to use implicit differentiation, there's really kind of some basic steps here. You're thinking about a couple things. So we're going to do an example. We're going to do the same thing we just did, but we're going to use the idea of implicit. So steps, first step, just basically assume we know y prime. Basically that it exists, and so there is some value that is y prime for this thing, this x squared plus y squared equals 1. We assume that there is such a thing. Okay. Then what we do, and this is the big difference here, is we just differentiate both sides of that equation that you see there. We differentiate both sides. So we differentiate the left side and we differentiate the right side. And then really the key thing is to remember that y is, I should say, I'll say it this way. Y is, hold on, there we go. Y is dependent on x. And what we mean by that is that when we take the derivative of something that has y, so like right here we have y squared. So when we take the derivative of that y squared, we don't just have 2y, because we have to use the idea of the chain rule. And if you had something squared and your job was to take the derivative of it, you would say, well, the chain rule tells me to bring down the 2, keep what I have the same, subtract 1 from the exponent, and then multiply it by the derivative of whatever that thing is. And that's the idea. Y is not, the derivative of y is not 1. The derivative of y is the derivative of y, and that is y prime. And if you can remember that, you can do implicit differentiation. So a lot of this is exactly what you think. When we take the derivative of 1, 1 is a constant. So the derivative of 1 is, derivative of any constant is 0. When you take the derivative over here on the other side, the derivative of x squared, still what you always think, 2x, just as we've always done. The only difference is, when we take the derivative of y squared, that is not just 2y. It's 2y times the derivative of y, which is y prime. Now that's technically true with x squared as well. Derivative of x squared is 2x times derivative of x, but the derivative of x is 1. So in order to now find the derivative of this, we would solve it for y prime. 2y times y prime, negative 2x. We have y prime equals negative 2x over 2y. And so we know that y prime equals negative x over y. But the key thing to see here is, well, first what we can do is, we already know what y is, because we were given that in the last, on the last page, that y is root 2 over 2 as well. So you can see that this tells us that y prime at root 2 over 2 is simply negative root 2 over 2 over root 2 over 2, or negative 1. But that's because if anyone was thinking, well, why we got the same answer, but I'm still confused, if this is what y prime is equal to, remember from the last page, we solved this for y. And at root 2 over 2, y was negative x over the square root of 1 minus x squared. But that's what y is. We've solved this thing. When you solve the unit circle for y at that value root 2 over 2, you get the square root of 1 minus x squared. That is what y is. But again, we can do these both ways because neither one is particularly challenging. X squared plus y squared equals 1 can be solved for y. Some of them can't. But we get the same thing. We find that we get, in fact, this negative 1 that we got the last time as well. So, don't forget that that is true because we're just using this idea from the last problem. It all connects together. So I think I will stop right there for this part, and then for part 2, I'll do all the examples that you see that are for the rest of this section.